In this tutorial, we will learn about how to design a 2:4 binary decoder digital circuit. So a 2:4 decoder will have two inputs A and B and four outputs Q0, Q1, Q2, Q3. Now the basic job of a decoder is to convert a binary input to its equivalent decimal. For example, if we consider this truth table, now 0, 0, if you convert to its binary, so it's 0. So only that time Q0 will be 1 and remaining all signals will be 0. If you take 0, 1 and if you convert it to decimal, it's 1. So only Q1 will be 1 and remaining all signals will be 0. Similarly, 1, 0 is 2 and 1, 1 is 3 and those signals are 1. Coming to their Boolean expressions, how we write is because Q0 was 1 at 0, 0, so we write it as A bar B bar. And Q1 was 1 at 0, 1, so we write it as A bar B. And similarly for Q2 and Q3. So now coming to its Verilog code, let us start coding this binary decoder. So let us start the Verilog code with the keyword module and give some name for this circuit like decoder. Next, what we need to do is declare all the signals which are present in our circuit. So there are two inputs A and B and there are four outputs. So that output I will now call it as Y and I will close this. Next, let us declare what are inputs and outputs. A comma B are inputs and output I will declare it as a 4-bit vector. So I'll write 3 down to 0 Y. Why I have written 3 down to 0 is because from 0, 1, 2, 3, we can store 4 bits of output in this. So instead of writing them separately like Y3, Y2, Y1, Y0, this is another way of declaring output as vector. Next, let us assign the output value. So assign, so first output, if you remember from your expression, was A bar B bar. So we need to write not of A because A bar is represented with not this symbol and not of B and put a semicolon. Similarly, I will copy this line 4 times and we will edit. So assign Y of 1 will be this time. So next expression was A bar B. So I have removed that not symbol. Next Y of 2 was A B bar. So I'll remove bar from this and A B bar. And last one Y of 3 was A ANDed with B. So I will remove not from both the gates. So after we have done giving the output expressions, we will end our code with end module. Every module beginning has to have a end module. So our design code is now completed. Let us now start writing a test bench code for this. So I'll start writing beside this and later we will copy and paste it on EDA playground. So declare the name as some module TB test bench and before itself you can write end module. Next you need to remember is whatever things were input, those will become reg in test bench. So reg A comma B and whatever thing was output, it becomes wire in test bench. So wire 3 down to 0 Y. Next you need to instantiate this code. So write down the name of the module decoder, write some name DUT and then call the signals in the same order as they are declared in this design code. So A comma B comma Y. You write it in the same order. A comma B comma Y. Because we are doing port connection by order. Next, you begin one initial begin block. Now the first thing we need to write here is two files related to generating the waveform. So we need to invoke dump.vcd, and next thing we need to write is $dump vars, and you write down 0 comma dot. Next we need to write one $monitor statement for printing of all the values of input and output, and we can print time also. So we'll write down so let me just scroll this so that we have more space. So we'll write time equal to percentage 0t. So 0 actually will remove the extra space, and t is specifically related to printing time. Next you can write down a equal to percentage b and b equal to percentage b, and y also equal to percentage b, and you can end the double quotes. Later time will be replaced with $time, and then a comma b comma y, and close the brackets and semicolon. Next you can start giving the different input combinations like a equal to 0, and then b equal to 0, and then some delay of 50 nanoseconds. So I'll call this 4 times and I'll edit the values. Next combination is 0 1, then 1 0, and last one is 1 1. After you have given all the combinations, you can call $finish. So our test bench is also now completed. So let us copy this test bench code and design code and paste it on EDA Playground for us to run. So I have copy pasted both test bench as well as design code. Let us go to tools and simulator and let us select Icarus Verilog and click on open EPWave after run to see the waveform, and let us hit on run to check if any syntax errors are there. So if you observe here, our code was successfully compiled, and if you observe like at a equal to 0, b equal to 0, so the numbering starts with 0 here, so only last y of 0 was 1, and 0 1 if you convert to decimal it is 1, so y of 1 is 1, and then 1 0 means 2, therefore y of 2 is 1, and 1 1 means 3, so y of 3, that is the third bit, is 1. So this was our printing of with the help of $monitor, and same thing we can also observe in our waveforms. So you can observe here that at 0 0, the first bit, that is the 0th bit, is 1, because 0 0 if you convert to decimal it is 0. Next if I click at 50, 0 1 means 1, therefore only first bit, because in programming numbering starts from 0. So this is the 0th bit, this is the first bit, this is the second bit, and last one is the third bit. Similarly, like for this 1 0 means 2, therefore second bit, and last one 1 1, 1 1 means 3, therefore the third bit was 1. So hopefully now you understood the decoder operation. Let me just show you the code once again. So you can take a screenshot of this code and try to replicate the same in your online Verilog compiler. Thanks for watching.